For this lesson, we're going to be taking a look at the more generic exponential function b to the x. And in a previous lesson, that's where I started. I started with b to the x, and then I moved from there to the natural number and the natural exponential function. So in a previous lesson, we ended up with y equals e to the x, and we talked about the properties of that. So for today's lesson, we're going to be continuing with that, and we're going to be using a bunch of the results that we got in that previous lesson. The first of those results is actually shown here. When we started with the function b to the x and we tried to find the derivative from first principles, so using a limit definition, the best we were able to come up with was this expression. So the derivative of b to the x is b to the x again, and then there's this multiplying factor, which is the limit as h approaches 0, b to the h minus 1 over h. But notice that nowhere in this extra factor is there an x, which means this actually is not a function itself. So there's no derivative I have to take here. It turns out this value will be a constant, but the value of this constant is going to depend on the value of b. So now our next challenge is to figure out if we want to take the limit of b to the x, we need to figure out what this constant is going to be. So one way that we do that, and this is a mathematical tool that's used, is we take ratios. So in this case, we're going to compare the ratio of the first derivative as compared to the original function. So that would mean I would end up with this whole expression divided by the original function. And as you can see, the thing that's going to disappear is b to the x over b to the x is just going to become 1. And so we're going to be left with just this limit. So now that we've isolated this limit, what does it actually mean? What kind of values can I figure out that go along with that? And as I did before, I'm going to enlist GeoGebra to help me try to figure that out. So let's start off with this. I'm going to let my b value be 2, which means f of x is 2 to the x. And I'm going to show you, I've got some screenshots of some graphs that I did previously. So I'm going to show you what kind of results we start to get if I go to GeoGebra. So here my b value is 2, so that's my function. It's y equals 2 to the x. My x coordinate is currently set to 0, so that's the point 0, 1. And so the y coordinate of that point, which is the function value at that point, is 1. That's 2 to the 0 equals 1. And the slope of this red dotted line, which is the tangent line, the slope of that is 0.69. So we have a y coordinate of 1 and a slope of 0.69. So if I went back here, I would say we had a y coordinate of 1 and a slope of 0.69. And then I could take the ratio of my slope to my y coordinate, and that ends up being 0.69 divided by 1, which of course is equal to 0.69. Sorry, that looks like 6.69. 0.69. Okay, now if I did 2 to the power 1, that's going to be 2. And if I now move my x coordinate to 1, 2 to the power 1 is equal to 2. So when the x coordinate is 1, the y coordinate is 2. And the slope is 1.39. So that would give me a slope here of 1.39. And I could continue to do that. I could change my x coordinate to be an x coordinate of 2 gives me a y coordinate of 4 and a slope of 2.77. So that gives me a y coordinate of 4 and a slope of 2.77, and so on. And if I continued filling this out using my GeoGebra page, I would end up with these results. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. The slope ends up being 0.69, 1.39, 2.77, 5.55. All of these are approximations based on the level of precision that GeoGebra gives me here. So there are going to be limitations, and I'm trying to be honest about that. As you can see, my ratio of the slopes is not always the same number because of those small inconsistencies due to the lack of precision. But you can see that they're all approximately 0.69. This one seems to be the one that's furthest away from there. But 0.69, 0.69375, etc. If I did the exact same experiment, but this time I used E, so E is the value 2.718, so I'm going to round that 2.72. If I take my x coordinate to 0, I end up with a y value of 1 and a slope of 1, so 1 over 1 is 1. If I go here, I end up with the slope 2.72 divided by the y coordinate 2.72. That's a ratio of 1. That's going to be a ratio of 1. And you can see, this is again, because of the lack of precision, it's not quite 1, but it's pretty close to being 1. So when I do the next one, and I put in my values, I put in e to the x, and I end up with 1, because e to the 0 is 1, and then e and e squared and e cubed. These are the slopes that I got, and the ratios more or less turned out to be 1. And finally, if I let f of x be 3 to the x, I ended up with a bunch of ratios that were about 1.1. So the ratios were constant, and that's a good thing. So that tells us that for any value of b, this ratio is constant. Essentially, this ratio depends only on my b value. So the question we want to know is there a function that we can do to represent this ratio? So remember, this ratio was the limit as h approaches 0 of b to the h minus 1 over h. So the question is there a function, is there some function that will give us that value? So is there some function that, depending on what value I put in here, whether it's 2 or e or 3, I end up getting these numbers? And so what we're going to do is we're going to focus on this result. G of e is equal to 1. What function is there? So let's say I'm creating some hypothetical function. So I'm trying to create this hypothetical function g of x. What function is there, g of x, so that when I put in my x value of e, I end up with a 1? And that's maybe not the easiest way to think of it. So let's ask it another way. What function with an input of 1 gives a result of e? And by asking you to think about it that other way, I'm playing around with the idea of functions and their inverses. So let's just isolate that idea, just that focus on e. So what I'm asking is, what function is there that when I give it a value of 1, I get the value of e? Well, one possibility there could be f of x equals e to the x. Right? That seems to make sense. If I put in 1 here, I end up with e to the power 1. F of 1 is equal to e to the power 1, which of course is equal to e. But that was the answer to this question. So, and I've already kind of said this part now. So how do I go from here up to here? And the answer is I need to consider the inverse. So in order to consider the inverse, what I'm going to do is, instead of writing f of x equals e to the x, I'm going to say y equals e to the x. And then for my inverse, what do? I'm going to write that. So if you look at this, this is in exponential notation. So this becomes x equals log base e of y. And then I will swap my x and y. I could have done the swap before or after. So my function y equals log base e of x. And so that means my function, this function we were looking for, g of x, is the log base e of x. So we've done logarithms before with various bases. We've never looked at really the base e, but that's what we have now. This actually has a special notation, just in the same way that e is a constant that has such importance in mathematics and in natural sciences. So does this have a special notation, and we call it the ln, which is ln of x. And this is known as the natural logarithm. So that's the natural logarithm of x. So I wanted to show you that just so you didn't feel like we were arriving at this with no foundation, with no justification at all. So here's the beginning of the note that we would be covering in class. So if you're using this to take down notes, this is a good place to pause and jot some of this down, because this is basically a summary of what we just went through without as much of the explanation. So if we have e to the x and we were to graph e to the x, we end up with an exponential graph. And that we know is a function. All exponential graphs are going to be functions, meaning they pass the vertical line test. But if this is a function, we should be able to take its inverse. So we can do that, and I showed you that in the previous pages. And if we take the inverse of this by swapping x and y coordinates, we actually end up with this red line. And that red line is also a function. It turns out that red line is a logarithmic function, and more specifically, that red line is the logarithm function to the base e. And it is known as, you can write it as log to the base e of x while you're getting used to this idea, but you want to transition to calling it the ln, the natural logarithm. And so the pronunciation is like the grassy lawn in front of your house. So that's g of x equals ln of x. So what we had before was that if we had an exponential function b to the x and we took the derivative, we ended up with the exponential function repeated multiplied by this factor. But this factor is actually the ln of the base of the exponential function. So whatever this value b is, we take the ln of that, and that's a number, that's a constant. So for example, if we start off just with f of x equals a generic b to the x, then f prime of x, normally we write constants first rather than last. Here it's written last. Normally we would write that first. So the derivative of b to the x is ln of b, the natural logarithm of this constant, of this b value, multiplied by the original function, the original exponential function, which is b to the x. We can also have a chain rule situation. So if we have b raised to some other function, the derivative is still going to be the ln of the base multiplied by the original function, but now because it's the chain rule, we also have to take the derivative of the function that was in the exponent. So this is an example of the chain rule for this particular situation. All right, let's go ahead and take a look at a couple of exercises that will illustrate this, at least hopefully. So the first one, f of x is equal to 7 to the x. So f prime of x, if we take the first derivative, that's going to be equal to the natural logarithm of the base, which is 7, so ln of 7. And I'm going to actually, since I'm doing this by hand, I'm just going to be really clear, especially our first time through here. This is ln of 7 multiplied by the original exponential function, 7 to the x. Now, quite often you will see this when it's written, particularly when it's written using typesetting in a document, you will see this as ln of 7 and then just 7 to the x. But there is the risk of ambiguity there. Does this mean the ln of 77 to the x? Does this mean the ln of 7 times 7 to the x? So whenever possible, whenever there's a chance of this ambiguity, we want to make sure that we're very clear. Okay, so this way, I think this is the best way to be clear about that. This is questionable, so I would avoid that because neither of those is actually the correct interpretation. How about this next one? This time I'm using xy notation, so we would write this as y prime is equal to the ln of 5, because that's the base, multiplied by the original exponential function, 5 to the exponent square root of x. But now I also have to multiply by the derivative of this. And if you need to, often maybe some separate work, square root of x is the same as x to the power 1/2. So the derivative, and now I'm going to use this Leibniz notation, d by dx of x to the 1/2, which is just another way of saying the derivative of x to the 1/2. That's equal to 1/2 x to the negative 1/2, which is equal to 1 over 2 square root x. So now I can take this result and I can put that right here, 1 over 2 square root x. And this I might actually clean up a bit, so I end up with y prime is equal to, let's see, I've got the constant, so I'm going to put in the numerator, I've got ln 5 multiplied by 5 to the square root of x, and then the denominator of the whole thing is 2 square root of x. And finally, we've got that third one, which I think I will just take a copy of over here. Actually, you know what? I'm just going to drag it down here, and then I'll work from here. And so I end up with, now this one's going to be a quotient rule. So I end up with g prime of x is equal to the derivative of the first, which is the derivative of this exponential part. So the derivative of that, now I'm going to write it this way just to show you how this is consistent with what we did before. It's going to be the derivative of the top, which is the ln of this base, which is ln of e, multiplied by the original function, e to the power x to the power 2, multiplied by the derivative of this, which is 2x, that's the derivative of the exponent, multiplied by the original denominator, which is 3 to the power x. And actually, I realize here I'm not going to have enough room if I do this over to the right, so I'm going to have to move this down here so that I can actually fit this on one line, minus the original numerator, which is e to the power x to the power 2, times the derivative of this denominator. The derivative of this denominator is going to be the ln of 3 multiplied by 3 to the x, and then we would chain rule this. What's the derivative of x? The derivative of x is just equal to 1. So this is why we don't actually need to apply the chain rule here. But if you did, there'd be nothing wrong with that. Over the bottom squared, which is 3 to the x, all squared. And now, let's finish this off. The ln of e, remember that ln is the same as log base e. So log base e of e is just equal to 1. Ln and e to the x are inverses of each other. They undo each other. So this piece is just equal to 1. Then I can bring some things in front. For example, I'm going to bring this 2x in front. And then I will write, now the order you do these is really irrelevant. So I'm going to write that as e to the x squared, 3 to the x. Minus, now this one, the constant is ln 3, and there's nothing I can do with that. I want to keep an exact value. E to the x squared, 3 to the x, all divided by 3 to the x to the 2, which is going to actually be 3 to the 2x, using one of our power rules. Now I could go further than this. There's some common factors here. There's a common factor in the denominator because we've got 3 to the x's, 3 to the x, and a 3 to the 2x. So there is some simplification I could do here, but I have achieved, so let's actually put a little notation here. I've achieved what I wanted to show you this, and then I could say dot, 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 which is you could simplify this further. And that is it for this lesson. So now we've covered both the natural exponential, e to the x, and we've covered a generic exponential, b to the x, and taken derivatives for both of them.